we talked about position and displacement, and then velocity and acceleration. Um, and so now we talked about the definitions of velocity and acceleration in terms of derivatives. So I want to just say something about going back and forth between acceleration functions, velocity functions, and position functions. Um, okay, so position is a function of time, velocity is a function of time, and acceleration is a function of time. This is important. Well, position, so let's think about like a velocity function. It's very possible that you could have a case where you know the velocity as a function of the position. Or maybe it's easier for me to come up with examples where you know the acceleration as a function of the position. Okay. So what if instead of being a of t, you have like a of y? Okay. Like the acceleration is determined by the height of the object. Well, I said that acceleration is the second time derivative of the position, right? But if you have the acceleration as a function of something that's not time, you can't just assume that. So acceleration is not equal to v prime, is not equal to p double prime. Okay. Those derivative relationships are just saying like, whatever function it is, whatever you have a function of for velocity or acceleration, take the derivative and it gives you acceleration. Okay. You can't do that. It's very important that that is a function of time. Okay. If it's not a function of time, you have to figure out some other way to do it. Sometimes you can work around with chain rule or whatever, but the relationship that we have is A is the time derivative of velocity, and the second time derivative of position has to be time. Okay. The independent variable has to be time. Okay, so there's sort of two possibilities here for going between these functions. The first one is if you're going in the direction of P to V or V to A. Okay. This is the easy one. You already have what you already have everything you need. All you need to do is take time derivatives. But there are times when we want to go in the other direction. So what if you're going in the direction A to V or V to P? Okay. Yeah, in that case, you don't have everything you need. Until you have one boundary condition for each level, and so like I'm getting ahead of myself. One boundary condition or for each step maybe. Okay, so if you're going from acceleration to velocity, that's one step. You're going to need one boundary condition. If you're going from acceleration to position, that's two steps. You're going to need two boundary conditions. The reason for this is in this direction, you're taking integrals with respect to time. And when you take integrals, you have constants of integration. And the boundary conditions let you solve for the constants of integration. So these boundary conditions let you solve for the constants of integration. So how does this work intuitively? Let's say that you're given velocity as a function of time for a flying object. And you're asked to calculate the height as a function of time. Well, based on the velocity, so I mean, if it starts out at 50 miles per hour going this way, and then it goes 30 miles an hour this way, and you have that velocity, but you don't have any knowledge of where the thing was when it started or where it is at any point in the motion. This could all be happening in outer space, or it could be happening starting a foot from the ground, and all that clearly has an effect on what the object's height is throughout its whole motion. So that's kind of the idea of these constants of integration, these boundary conditions. If you're given the height at time equals 0 is the most common, but if you're given the height at some time, then you can figure out for the rest of the motion how high it's going to be. Okay. So in order to do this calculation, you need to know the height at some specific time. And that's the boundary condition. Okay, so let me do an example. So let's say you're given that velocity as a function of time is equal to 3t squared. And at time equals, let's say at time equals 1 second, the position is 5 meters. What's the acceleration as a function of time? And what's the position as a function of time? Okay, well, the one where you don't need any additional information, just knowing the function is enough, is going in the direction of velocity to acceleration. All you're doing is taking the time derivative. So the acceleration is the time derivative of the velocity, and so that's 6t. The position, though, the position is the integral of the velocity with respect to time. So integral of 3t squared dt. Yep, and so that's t to the third plus this constant c. Okay, and now that's where we're going to use this boundary condition to calculate c, because we know that when time is equal to 1 second, this function representing the position has to be equal to 5. Okay, so the boundary condition says 5 is equal to 1 cubed plus c. So c is equal to 4. And so then the position as a function of time is equal to t cubed plus 4. So now let's say that we want to know, well, let me look at this function. Okay, so how about, is the object ever slowing down? Remember, an object slowing down if the velocity and the acceleration are opposite directions, opposite signs. So we want to check the signs of v and a. Okay, so velocity, is velocity ever negative? That can't be, even if time were negative, because time is squared. So velocity is always positive. Is acceleration ever negative?
Whenever time is
right. And in this class, we're never going to deal with negative times. So it's always speeding up. And it's always speeding up in the positive direction because the velocity tells you the direction it's moving. Okay, so there's a special case that we're going to deal with pretty often. Constant acceleration. And the most important case of constant acceleration is free fall or projectile motion. I'm going to use those interchangeably. For an object with negligible air resistance. Okay, so what we're going to do is we're going to say if the acceleration is a, and that's a constant, that's not a, in this case, that's not a function of time. And if the velocity at time 0 is v0, and the position at time 0 is p0, we're going to derive equations for position as a function of time and velocity as a function of time. Okay, so the first step, we know that the velocity is the integral of a dt. That's what we had before. The only difference is this time that a is a constant. We don't have to worry about that being a function. So when you integrate this, you get at plus c. And now we'll use the boundary condition to calculate that constant c. So what do we know that we can use to calculate that c? We know that if you plug t equals 0 into this equation for v, then v is this constant v0. Okay, these are both constants too. Okay, so we know that when t is equal to 0, v is equal to v0, so we have this equation. And so that tells us that c is equal to v0. And so velocity as a function of time is equal to at plus v0. Most often, I mean, almost always when you see this, it's going to be written in the other order. So I'm just moving it around to match what you'll see. But there's our first equation for velocity as a function of time. That's only if you have a constant acceleration a. And now we want to do the same thing for the position function. So position as a function of time is the integral of the velocity as a function of time with respect to time. And we have a function for that now. So this is the integral of the quantity v0 plus at dt. And so that's v0t plus AT squared over 2 plus, I guess I'll call this C2. And again, we have this unknown constant of integration. We have to use the boundary condition to find that. And the boundary condition that matters for this one says if time is equal to 0, position is this constant P0. So we have P0 is equal to V0 times 0 plus A over 2 times 0 squared plus C2. So C2 is equal to P0. And so the position as a function of time is equal to, I'm going to rearrange it to make it the way that you normally see this, P0 plus V0t plus 1/2 a t squared. There's a third equation. I mean, you could derive all sorts of equations, but it's often useful to have a relationship between A, V, and P that doesn't depend on T. So we're going to use the equation from 2 and the equation from 3 and just eliminate time. We're going to combine those two equations using substitution. So we'll use substitution to eliminate the explicit dependence on time. Uh, 1 and 2, I guess. Okay, so our two equations that we're going to start with are V is equal to V0 plus AT, and P is equal to P0 plus V0t, sorry, plus 1/2 a t squared. And let's keep track of what are constants and what are functions, because I didn't write it explicitly with the function notation. What about V and P? Are those constants or functions? Those are functions of time. And then all the rest of these are, this is a constant, constant, constant. Okay. And so on. These are all constants. Okay, so I'm going to use the simpler of these two equations and come up with an expression for time, and then I'm going to substitute that into the second one. So from the first one, we have V minus V0 divided by A is equal to time. and then substitute that into the second one. So we have P, let me write a note here. So this is from equation 1. And so P is equal to P0 plus V0 times the quantity V minus V0 over A. And then plus 1/2 times A times V minus V0 squared over A squared. That's already an expression, that relates these variables without time in it, but we can make it look a lot cleaner. So let's cancel this A and one of those two A's. And I'll write this as P is equal to, let's just get the whole thing over A for now. So we have P0A plus V0V. This whole thing is going to have a denominator of A. V0V minus V0 squared plus 1, actually, let me multiply all this stuff by 2. So there's a 2, there's a 2, there's a 2, just to get this half to go away. So we have a 2 here, a 2 here, a 2 here. And now squaring this out, FOIL, we have V squared minus 2 V0 minus V0 squared. This should have a 2 also. Okay. Anybody lost or behind? Understand what I'm doing here? So all I did was substitute, and now I'm just looking for a way to simplify this. I multiplied both sides by 2 to get rid of the half. And now we're going to see some cancellations happen. We have, let's see, plus V0V minus, plus 2 V0V minus 2 V0V. So these go away. And this should be plus. I FOILed it out wrong. And so that means that this 2 goes away and becomes a 1 and cancels that. And so we have 2PA, multiply the A to both sides, is equal to 2P0A minus V0 squared plus V squared, and that's it. So now I'm going to subtract this first term from both sides, and you can write that as 2 times A times the quantity P minus P0 is equal to V squared minus V0 squared. And I'll call that, the third of these equations. So the things that you need to keep in mind are these two are functions of time, even though we don't have an explicit dependence on time. Those have to be at the same time t. Okay, those have to represent the same instant. And then this and this and this are constants. Okay, so let me do an example with this. So let's say we have a ball rolling on a ramp. And let's say when it passes the point A, it's going 1 meter per second. When it gets to the point B, it's going 2 meters per second. And let's say the distance between these 2 points is 1 meter. What's the acceleration of the ball? So this is a case where the acceleration is going to be constant the whole time. That's just something it's not obvious that would be true, but it just happens to be true. We'll do labs where we see that. Okay, so how are we going to calculate this? It's constant acceleration, so we know all three of those equations apply. And we first have to choose an instant that corresponds to time equals 0, a location that corresponds to the 0 position, a positive direction, and an instant corresponding to time t. Okay, where we want to calculate stuff. And these two times, we want to choose these based on when we know stuff and or when we want stuff. Okay, so where do we have information in this problem?
We have the speed at point A and point B.
Right, we know we have information at when it passes A and when it passes B. So right at the start, we would naturally think our time equals 0 is probably going to be when it passes A, and our time t is going to be when it passes B. We only have two choices for these important times. And time t has to be later than 0 because we can't have negative times. And then as long as that works with where we're trying to calculate stuff, then we're good with those. So where are we trying to calculate stuff? In this case, what we're trying to calculate is acceleration, so it holds for the whole thing. Okay. In other problems, we'll be trying to calculate like a velocity or a position at a single point. And so in that case, you'd have to have one of your two instants be the place where you're trying to calculate stuff. You can't calculate something. You can't calculate a variable that isn't in your equation, you know. So, all right, well, let's put down the 0 position. This is arbitrary. We just have to be consistent through the whole problem. I think most people would probably choose 0 position to be at A, but you don't have to. And then positive direction. Most people would choose downhill, but I'm going to choose uphill just so you see sort of how the signs work in this. Okay, so based on that, let's think about the information that we know, okay? So what do we know and want out of our checklist of possible variables? And that is T, A, P0, P, V0, and V. Okay, those are all the variables that appear in those three constant acceleration equations. Yeah, so we know that, so time we don't know. We don't know how long it takes to get from A to B. Acceleration is what we're trying to find. At time equals 0, what's the position of this object? So time equals 0 is when it passes A. So what's its position? That's right. So P0 is 0. What about P at time t? Do we know that? Yeah, very good. So think about that for a second. So we know that the distance between A and B is 1 meter. Okay. And we know that if you start at 0 and go 1 meter in the negative direction, your position is -1. Okay. So in this case, our P is -1. Okay, and then keep going through the list. What about V0? Do we know the velocity at the instant the ball passes A? Yes, so we know that the speed is 1 meter per second. The direction is down the ramp, which is in the negative direction. And so V0 is -1. I guess I'll put units on these. This is -1 meter. This is -1 meter per second. And then what about the velocity when it passes the point B? That's right. Yep. So V is equal to -2 meters per second. And so now all we have to do is find an equation that lets us work with this. So find an equation that has the wanted variable, because you can't solve for something that's not in the equation. And has no other unknown variables. Okay, so is there, of these three equations, I can't get them all up on the screen right now. So this one, the V equation, the P equation, and the one that doesn't use time. Let me write these down here. So this is out of our three equations. V is equal to V0 plus AT. P is equal to P0 plus V0t plus 1/2 AT squared. And then the last one says 2A times the quantity P minus P0 is equal to V squared minus V0 squared. So is there one of those three equations that is going to work with this to let us calculate A? The last one, yep. So we have 2A times the quantity -1 minus 0 is equal to -2. And then you square that whole thing. That's an order of operations thing. Minus the velocity -1 all squared. And so you get -2A is equal to 4 minus 1. And so A is equal to -1.5 meters per second squared. Okay, so at some point during this, so intuitively, what does this say is going on? So at some point in the path, our positive direction is up, right? Our velocities are both negative, and our acceleration is negative. Okay, so we have negative answers for velocity and acceleration. So which direction is the object moving, up or down the ramp? Yep, so there's the direction of the velocity. And is it accelerating up or down the ramp? Down. So it's speeding up, since those are the same direction. Down the ramp. Okay, what if, this is the last question here. What if when I did this problem, I had put the positive direction the way you all said, and the way, if I really saw this problem, I would do it myself too. What if I had put the positive direction down? What would change in all this? It would change all the signs. Okay, so it would change all the signs. What about the meaning at the end? So they would be the same. Do you see that? Because now our positive direction would be this way. We would have calculated positive velocities and accelerations. And even though the answers numerically would look different, they would tell the same physical story. This, and obviously there'd be a big problem if it didn't, because a ball, just because you choose your positive direction one way doesn't start rolling up a hill, So it would tell the same physical story with different numbers corresponding to your different choices.